Hello, this video covers the material on the function notation power focus area, for which you need to know three things: functions, about domain and range, and piecewise functions. Function? What is a function? A function is a relationship or expression where each input only has one output. And what you need to remember from that is that every x only has one y. This means that every x is unique, giving a new answer. So every time you choose to plug in a value for x, not only do you get an answer, but you get one answer. You can't get two answers because that would mean it's not a function. And if you plug in a number and you don't get an answer at all, then you're not allowed to plug in that number. That number is not a part of the domain, but more on that later. No, I meant like, what is a function? As in, can you point to one? Can you show me what one looks like? What are we doing here? A function could be represented in lots of different ways. It could look like a graph. A function could be a table. A function could be an equation. A function could be a list of points. A function could be a mapping. A function could be piecewise. Or a function could be a rule. These function rules say, at this dealership, green cars are expensive. Input green car, output price expensive. All of the students who persevere will pass this assessment. Input student who perseveres, output pass the assessment. On my birthday, we go bowling or we have a dance party. Input birthday, output bowling or dance party. When you look at these, it's okay if you don't know anything about the equation. It's okay if you don't recognize the properties, or you don't have to do anything with this. I'm not asking you for an answer that's a number or for you to do any math with this. The main thing I'm asking you to do right now is to look at it and identify whether or not it's a function. So if you recognize some of the different parent functions, that's definitely going to help you, right? It turns out that this is the parent function, and it's not quite this graph because it's been shifted over a little bit. But if you recognize that this is a line, okay, that this is the inverse of a parabola, and even when you look at these, maybe you recognize some of the rules. Maybe you will, maybe you won't. Here, it's easy to see the rule. It's adding 4. Here, this is the graph of sine x. Okay? And this one doesn't have a rule here. You might not be able to look at it and recognize the rule. But that's okay. You don't have to recognize the rules to do this. We're just deciding whether or not it's a function. So all of these are functions then? Are they all functions? Nope, they're not all functions. I've put an example in each category of something that's not a function. Remember, a function is something where every x has only one y. So let's look at y. Which one of these is not a function? This one is not. The reason that this is not a function is because this x value right here, where I've drawn the blue line, has 2 y values. It has a y value right here and a y value right here. So that means that this fails the vertical line test, which means that it's not a function. Which one of these tables is not a function? Here, I can see that the zeros repeat, that there's an x value that has 0, and that there's another x value here that also has 0. But that's perfectly okay, because we don't care about 2 y values. We need to see whether or not every x value only has 1 y value. So it's the x's that cannot repeat. So as I look at these, this one is not a function. And the reason it's not a function is because the reason that this one is not a function is because the x value of 2 repeats twice, And each time the value of 2 goes to a different y value. That's one x value, 2, going to two different y values, 7 and 5, not a function. How about these equations? Which one of these equations is not a function? There's no really restrictions that we have to look at here with functions. The only thing to look out for is when we have a y squared. Okay? When we have a y squared in here, it's going to make two possible values for y, so this is not a function. And if we were to graph this, it would be a circle with a radius of 3. This is an equation for a circle with a radius of 3, and that would definitely let us know that it's not a function. What about these sets of points? Which one of them is not a function? This one's not a function because here I can see that the x value of 0 is here and here, so the same x value is repeated twice, making it not a function. Which one of these mappings does not represent a function? It's perfectly fine that these two x values are going to the same y value. That's fine. But over here, we have the same x value. We have one x going to two different y's. So this is not a function. Which of these piecewise graphs is not a function? Here, this one is not a function because if I draw my vertical line again, I have two dots here, and they're both colored in. Now, if this graph would have had one dot open and one dot closed, so that this is the actual point and it's not actually hitting that point, that would have been fine. But since both dots are colored in, it is not a function. And here for the rules. This last rule, on my birthday, I don't know if I'm going to go bowling or have a dance party. Since I have two different options of what could possibly happen on my one birthday, then that means that this one would not be a function. But this video is called function notation, not just about functions. So why? Function notation is a special format for writing functions in equation form, where it uses the name of the function, the variable that the function will depend on, and then the rule of the function goes on the right-hand side. Fine, so then what were you saying about functions working and not working sometimes, or maybe not getting an answer? All the things that you can plug in that do work are in the domain. But if there are any values that don't work when you plug them in, then those are not in the domain. Like cars from other dealerships, or students who didn't persevere, or days that are not my birthday. Those things are not in the domain of what we're talking about. Then what is domain? I mean in a mathematical sense. The domain is the set of all x values that work when you input them in the function. If you look at the graph, the domain are the numbers that are covered by the graph looking from left to right. Two things to remember when you're trying to find the domain. No negatives are allowed under the square root. You can't take a square root of negative. And no 0 in the denominator of any fraction. When you're writing your answer for the domain, your answer can be written in a couple different ways. You could have a range. You could write your answer as an inequality. Or the answer for the domain could be a list. It's interesting to note that these two things are really saying the same thing. Though they're both saying that the domain is anything from 3 all the way to infinity. But this one is saying something different. The second one is saying that the only points that are in the domain are these separate values. Compare that with the inequality. Now this says that it's not just these 3 dots, but that it could also be anything, any of the values in between those dots. So these are disjoint values, whereas an inequality is everything between those values as well. We won't do the domain for all of them, but let's go ahead through and look at a couple examples of domain. For here, domain, we're looking at how far the graph is going to the left and to the right. And here I can see that it goes from negative infinity to infinity. Here, the domain going from left to right, it is going to go from negative infinity to infinity, but there's this one spot here that's not going, the asymptote here is not going to be included in the domain. In that case, 2 would not be included in the domain. The domain would be from this point over. This is the farthest to the left it goes is negative 3, and then it goes to infinity. Here, the domain is just listing the x values. So now I have disjoint values. The domain are these values are the domain. When you're looking at domain for functions, there's two things to look out for. One is that you cannot have a 0 in the denominator. To see what would make it 0, solve for x in the denominator. That tells us that the domain does not include negative 1. For these kind, to find the domain, again, we're just listing the x values. The x values are the domain. For mapping, the domain are the numbers that you're starting with, the input numbers. So the values in the first circle are the domain. On this, looking at the domain, how far it goes left to right, on this side it comes to negative 3, and over here it comes to 4. You have to look up how these brackets are working. The 3 is not included because of the open circle, so I have a parenthesis. But since the 4 has a colored in dot on it, that's why I have a square bracket. The range are the y values, the output. These are the things that are covered by the graph going up and down. Sometimes when we're looking at range, it's good to keep the parent function shapes in mind. For instance, if I have x squared, I know that it's going to look like a parabola. Whatever the function is, whatever's outside of the function, if it has a +2 or a -2, that's going to move the graph up or down. See, here I moved it up 2, which changes the range of how low and how high the graph is going. Sometimes range can have some other properties, some other exclusions on range that happen when there are holes in the graph or if there's a horizontal asymptote. But we're not going to worry about any of those things for range. None of those are on this particular assessment. The only thing I would like you to be able to do when it comes to these equations is recognize when the parent functions have been moved. By 2, then that shifts the graph up. And then I want you to be able to see how that affects the range. This graph is going to continue to go lower as the line extends. So again, we're going to go from negative infinity to infinity. On this one, it looks like the range is only coming down to about here. It's never going below 0. I could also say the range is x is greater than 0. Either one is right. When you're giving the range of a t-table, you can just list the y values. There's no need to repeat 0, even though it shows up twice. I thought the hardest part was piecewise functions because it really combines all these concepts together. A piecewise function is made up of multiple functions, each having a piece of the domain. These are the functions, these are the domain. You can tell it's a piecewise function because the graph has chopped up in pieces. There are two things that you need to be able to do with piecewise functions. You should be able to read the values from the graph, and you should be able to graph them yourself. To find the values from the graph, let's do that first. So if we're going to find the value f of -4 from the graph, it depends on what they give you. Here they're giving me the input value, the x. So since they're giving me the input x value, I'm going to come to my x-axis, and I'm going to come to -4. After I find -4, then I just come up the graph to see how high the function is there. And I can see at -4, the function is 2 squares high. On the other hand, if they give me the output value here, if I've given the output value of -3, that's my range, those are my y values. So now I'm going to come to the y-axis down to -3, and I'm going to see what is the function when I'm at -3. And at -3, I can see that I am right here at the x value is +3. Then, if I want to find -10, -10 is not goes off of my graph. So instead of using my graph, I can also use the function. What I have to do is figure out which piece I need to plug the -10 into. So I look at the domain and I see which piece of the domain is -10. Is -10 less than 2? Is -10 between 2 and 5? Or is -10 greater than 5? Since it's less than 2, I plug -10 into this part to get the answer. F of -10 is -1. But how do I graph piecewise functions if they don't already give the graph to you? When you're graphing piecewise functions, there are 3 things to keep in mind. The first thing you're going to do is the things that you remember about y equals mx plus b. Just plot the points where the line goes. Then you're only going to draw the part of the function, whether or not it's whatever type of function it is, you're only going to draw the part that covers the piece of the domain that you're talking about. So you look at this part, that's the only part you're going to draw. And then lastly, the endpoints. You need a shaded in dot for less than or equal to, or greater than or equal to, and an open dot for greater than or less than.
For the first line, the y-intercept is +1 and the slope is -2.
Next, only draw the part of the line that's part of the domain. The domain is cut at -1. Now, from here, I'm only going to draw the part that's less than -. Lastly, the endpoints. What kind of an endpoint do I need here? Less than is.
Looking at my second line, the y-intercept is -2 and the slope is 1/2.
This is greater than -1. So here's -1.
I see greater than -1 would be on this side. So greater than -1, I'm going to come down to my function. And then from here, I'm going to draw my line. What kind of a dot do I need at the endpoint of -1 this time?
It just has less than but no equal to, so leave that dot open. All right, and so that was our summation of functions and function notation. Please watch this video before taking the assessment.